On July 25, 1944, a British Mosquito reconnaissance pilot was flying high over Munich when he saw something impossible. A strange aircraft without propellers appeared behind him. It didn't just catch him, it flew past him as if he were standing still. The Allied pilot was flying at 400 miles per hour. The German plane was doing 540. This was the Messerschmitt Me-262's Schwalbe. It was the world's first operational jet fighter. On paper, it was the weapon that could reset the air war. It was 100 miles per hour faster than the P-51 Mustang. It carried 4 30mm cannons that could disintegrate a bomber with a single burst. But there was a statistic that the German propaganda ministry never mentioned. The average lifespan of the engines powering this miracle weapon was just 25 hours. In combat conditions, it was often as low as 10 hours. Imagine buying a Formula One car, but the engine melts every time you drive from New York to Philadelphia. That was the reality of the Me-262's. It was a masterpiece of aerodynamics, betrayed by the limitations of metallurgy and the collapse of the German economy. Today we are going to look inside the cowling of the Me-262's. We will ignore the dogfights and focus on the thermodynamics. We will analyze why the Junkers Jumo 004 engine was a ticking time bomb, how a shortage of rare metals forced engineers to build turbines out of tin cans, and why the fastest plane in the sky was most vulnerable when it was trying to land. To understand why the Me-262 failed, we first have to understand the physics wall that Germany hit in 1942. By the middle of the war, propeller planes had reached their limit. If you spin a propeller too fast, the tips of the blades break the sound barrier. This creates shock waves that destroy lift and shake the aircraft apart. To go faster than 450 miles per hour, you need to ditch the propeller. You need a jet. The German engineer Anselm Franz designed the Jumo 004 engine to solve this. It was a marvel of axial flow compression. It sucked air in, squeezed it, mixed it with fuel, and blasted it out the back. But a jet engine is essentially a continuous explosion held inside a metal tube. The internal temperatures reach 800 degrees Celsius. To build a turbine that can spin at 8,700 RPM in that heat, you need superalloys, you need nickel, you need chromium, you need molybdenum. Here is the economic bottleneck. By 1944, Germany had none of these. The Allies had bombed the supply lines and cut off trade with countries that produced rare earth metals. So, the engineers at Junkers were given an impossible task: build a jet engine using plain low-grade steel. This leads us to technical failure number 1, the hollow blade. Since they couldn't use heat-resistant alloys, the engineers had to be creative. They designed the turbine blades to be hollow. Inside the engine, they routed cool air from the compressor to flow through the inside of the turbine blades and out of tiny holes in the tips. It was air cooling from the inside out. It was brilliant engineering. It allowed cheap steel to survive temperatures that should have melted it. But survive is a generous word. The steel was coated in a thin layer of aluminum to prevent oxidation, essentially a high-tech tin can. Under the stress of combat, this coating would flake off, the steel would oxidize, become brittle, and then, boom. A turbine blade would snap at 500 miles per hour, tearing the engine apart and sending shrapnel through the wing. This is why the engines had to be replaced after 25 hours. The pilots were essentially flying disposable airplanes. This brings us to technical failure number 2, the throttle deathtrap. If you are a pilot in a P-51 Mustang and you get jumped by an enemy, you slam the throttle forward to get maximum power. It is an instinct, and that Me-262's, that instinct would kill you. The Jumo 004 engine used a primitive fuel injection system. If you jammed the throttle forward too quickly, the fuel pump would dump too much fuel into the combustion chamber before the air compressor could spin up to match it. This caused 2 things. First, the temperature would spike, melting the turbine blades instantly. Second, the compressor would stall. The airflow would reverse, and the engine would flame out. So, while an American pilot could fly aggressively, a German jet pilot had to operate his throttle with the delicacy of a safe cracker. It took roughly 8 to 10 seconds to spool the engine from idle to full power. In a dogfight, 10 seconds is an eternity. If you slowed down to turn, you couldn't just speed up again. You were a sitting duck until your turbines decided to cooperate. This throttle limitation dictated the tactics. The Me-262 could not dogfight. It had to fly straight, dive on the bombers, fire, and use its speed to escape. It was a sniper, not a brawler. Technical failure number 3. The starter motor. How do you start a jet engine in 1944? You can't just turn a key. The main turbines need to be spinning at a high RPM before the jet fuel will ignite. To solve this, the Germans installed a completely separate engine inside the jet engine. Hidden in the nose cone of the engine pod was a small, 2-stroke piston engine, basically a chainsaw motor called the Riedel starter. To start the jet, a mechanic, or the pilot, had to pull a cable like a lawnmower to start the Riedel motor. Then, the Riedel motor would spin the main turbine up to speed. Only then could you introduce the jet fuel. This system was comically unreliable. It often failed in the cold Russian winter, and it added weight and complexity to an already fragile machine. It represents the Frankenstein nature of Nazi engineering, a futuristic jet turbine started by a lawnmower pull cord. Now let's look at the logistics of the runway. The Me-262 was a tricycle gear aircraft. It had a nose wheel. This was modern, but the engines pointed slightly downward. When the pilots applied full power for takeoff, the exhaust blasted the ground behind them at 1,000 miles per hour. Germany's standard airfields were grass or asphalt. The jet exhaust would set the grass on fire or melt the asphalt into sticky tar. The Me-262 required concrete runways. This was a strategic disaster. Concrete runways are bright, white lines that are easily visible from space. Allied bombers knew exactly where every Me-262 base was. They didn't need to fight the jets in the air, they just bombed the concrete runways. This led to the rat-catching tactic. Allied fighter pilots realized they couldn't catch the Me-262 at full speed, so they loitered high above the known concrete airfields. They waited for the jets to return from a mission. When a Me-262 came into land, it was low on fuel. It had to slow down to 150 miles per hour. And remember the throttle problem? The pilot couldn't accelerate quickly if he was attacked. He was helpless. American Mustangs and Thunderbolts would dive on the landing jets and slaughter them. The technological advantage of 100 mph evaporated the moment the wheels dropped. There is a famous story of the top German ace, Walter Nowotny. He took off to intercept bombers, but his engines failed or were damaged. As he tried to limp back to base, he was caught by American fighters and killed. The technology that made him the fastest man in the sky also made him the most vulnerable. Let's talk about the fuel. The Me-262 didn't use high-octane gasoline like piston planes. It used J2, a heavy diesel-like fuel derived from coal. On the positive side, this was brilliant because Germany was running out of oil but had plenty of coal. Synthetic fuel plants could produce J2 cheaply. On the negative side, J2 was dirty. It clogged the fuel lines and nozzles, and because the Jumo 04 engines were so thirsty, the plane had to carry a massive amount of it. The Me-262 had fuel tanks everywhere, in the fuselage, behind the pilot, in the wings. This affected the center of gravity. As the fuel burned off, the balance of the plane shifted. The pilot had to constantly adjust the trim of the aircraft to keep it flying level. If he forgot to flip a switch to transfer fuel from the rear tank to the front tank, the nose would pitch up, the plane would stall, and he would crash. It was a plane that required you to be an engineer while you were being shot at. So, was the Me-262 a failure? Technically, no. It was a breakthrough. It proved that the jet age was possible. The swept-wing design was copied by both the Americans for the F-86 Sabre and the Soviets for the MiG-15. Every modern airliner you fly in today traces its DNA back to the aerodynamic research of the Me-262. But strategically, yes, it was a failure. It was a weapon that required a perfect ecosystem to function. Long concrete runways, highly trained pilots, rare metals, and careful maintenance. By 1944, Germany had none of these things. They put a Ferrari into a demolition derby. They built 1,430 of them, but only about 200 ever saw combat at the same time. Most were destroyed on the ground, lost in accidents, or sat in factories waiting for engines that never arrived. The Me-262 is the ultimate example of wonder weapon syndrome. Nazi leadership believed that a superior machine could overcome inferior logistics. They were wrong. A reliable P-51 Mustang that costs $50,000 and runs on standard gas is infinitely more valuable than a $1 million jet that melts its own engine after 10 hours. In the end, the Me-262 didn't change the outcome of the war by a single day. It just consumed resources that Germany couldn't afford to lose, to build a legend that couldn't stay in the air. So, here is the question for the comments section. If you were a German engineer in 1943, would you have pushed to mass-produce the Me-262 with these flawed engines? Or would you have focused on improving the piston engine Focke-Wulf 190, which was reliable and lethal? Let me know your choice below. And if you want to see another example of German engineering that was too advanced for its own good, check out our video on the V2 rocket, the space-age weapon that killed more people in its own production than it did in London.